last video here, and it's last because 40 through 44 are all about this graph here. So I'm just going to be referring to this graph to answer all these. Alright, so some key things. They're about the graph shown at the right with rational coefficients and its fifth degree. Okay, right away that in your brain should say there's 5 solutions to this. Some of them could be duplicates. But even if when we count all the duplicates and all the unique ones, we should end up with a total of 5. So when I look at this graph, this is my x-axis. You can see there's the 3 is marked. I think that's 3. No, it isn't. So this is 1, 2, 3. This is 4. This is 5 right here. So that's my x-axis. Let's see here. Where's my y-axis? My y-axis is running right up through the middle. It looks like it's at 50 and then 100. And then 150 up here. Alright, so this x-axis is kind of important to us. Right, this is where our solutions show up, and we think there should be 5 of them right now. And I can see there's one of them. I can see this one where it bounces, that counts twice. Once on the way down and once on the way up, so that's a multiplicity. So there's one answer, this is 2 and 3 are both 4. If I was going to list an answer list for this thing, I'd say it's -3, it's 4, and it's also 4 again because of that. When it just touches the x-axis, you get multiplicity, which means an answer happens more than once. Alright, so let's get into now, at most, how many imaginary solutions does this have? Well, at most, because it's fifth degree, it could have 4 imaginary solutions. Now, why could it have 4 imaginary? Because they always have to come in these pairs that we talked about previously. And so if you get one imaginary solution, you have to get its conjugate. And if you get a second imaginary solution, you have to get its conjugate. Okay, so they always come in pairs. So at most, it could have 4. Now, because I can see 3 of them right here, it doesn't have 4. At most, it can have 2 imaginary solutions. It can't have 4 because 3 of them we already know are real, because we could list those. So at most, it has 2 imaginary solutions. Identify the local maximum. So now I'm on question number 42. Identify the local maximum and minimums of it. Let's see here. Well, here's a maximum. There's a highest point. But that's an absolute maximum, not a local. Locals are ones that are just high compared to points around them. So this actually has 2 local maximums. One of them is also an absolute maximum. Okay, but they are both locals, as well as this one being 2 things. Looks like it is 181.178 and 100. So the highest it goes is 180. What was that? 181.178. It's the highest up at the top one, and then it has another maximum of 100. Now those are what we call local maximums. This one's an absolute, and it can be local. So relative to the things around it, it's also a highest point, but it's also a highest point. Oh gosh, it's not an absolute max. My bad. Sorry. It's not an absolute max because it goes on up here, so it does have higher points and it does have lower points. So it's still just a local max. So we're just fine. We don't have to talk about absolutes at all. Number 43, describe the inequality with an inequality, the x values when p of x is decreasing. All right, so p of x is the graph. When they're asking, hey, where is it decreasing? They're saying where are the y values going up and where are the y's going down. If they're going down, it's decreasing. So I'm going to get out my red highlighter. Well, I'm going to get out my blue first. So here, as my x's go to the right, I'm going up, 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 till I hit that maximum right there. And now I'm decreasing. All right, so it's that stretch of it right there. Now I'm going to erase a little bit of my stuff here so I can really dig in. All right, so here's my decreasing region. And we need to describe that with the x values. So let's find out his x value up here. It starts when x is negative 2.095. That's when I start to decrease. And I stop decreasing when x is at 0.095, it looks like. And then I start to go into this region of increase. But I just want to know where it's decreasing. And so I'm going to describe that but with the x values. I'm going to say when x was between, and I should do this in green because these are those green x values. See, the highest x was 0.095, and the lowest x was negative 2.095. So there's the interval. You could write it this way if you're using interval notation. It means the same thing as this one. Notice where those inequalities are. Saying x is bigger than that number, x is smaller than that one. So there's where it's decreasing. Let's see, I think there's some more decreasing though. Because I do this purple stretch, I started to go to increase, but now I'm going downhill again, so I'm decreasing. Okay, I'll trace it in green and we'll find out his x values. Let's see, it starts right there when x is 2. And it stopped decreasing when x was right there when x is 4. So we'll put it's decreasing there, and we'll put it's decreasing between, and again, high number on the right, small number on the left, point your inequalities left. So when you read from x's point of view, it says x is bigger than 2, x is less than 4. And that's where it's decreasing. Those two sections, if I wrote that part as an interval, it'd be 2 and 4 just like that. So there's the decreasing regions. And then our last little section, our last question, described with an inequality, when is the function greater than 0? So I'm going to erase a bunch of my stuff here on my graph. Let's see here. Well, we've already done where does it equal. Let me erase a little more carefully here. So we've already done this part. When does it equal exactly 0? Right there at the negative 3, right here at the 4. Oops, not the 4 there. The 4 right here. So there's where it equals 0. So when is it greater than 0? Well, it's always greater than 0 right here. I'm above the x-axis, so these are all positive y values. These are all positive y values. These are all positive y values, positive y values. Oh, y value of 0, positive y values. So this thing is basically always positive y values, except over here, like when I'm below that, when I'm to the left of negative 3 here, I'm going to be down here. So basically, every point in between here and, gosh, all the way to infinity, once I get past x is negative 3, positive y's, 0 y, then positive y's again forever. Its end behavior. As x goes this way, it continually goes up. And since it's positive, it will stay positive. So let's see if we could write how this would be. So the x's have to be greater than negative 3. And as long as they're greater than negative 3, my y values will always be positive numbers, except for right here at 4. So x is greater than negative 3, and x does not equal 4 is one way we could just write that. Okay. Another way we could write that to be a little more eloquent with it, is we'd write like, let me think here. Gosh, this would be kind of cumbersome actually, but we'd go like from negative 3 all the way up to 4. And then we'd skip over the 4. We use this little union symbol to infinity. So we'd write it like that. As an inequality, I guess this is kind of your best choice. We'd go like this. X is greater than negative 3, but less than 4. Or x is then greater than 4. And what this would do, if you think about a number line, how this would look. X is greater than negative 3 would start getting you this way. But it has to stay less than 4, so you'd have an open circle at 4. And then you'd pick it up again at 4 and say, hey, now I'm greater than 4. And so it would give you a graph of all the numbers you could do with a whole use with everybody greater than negative 3, but you'd have this hole at 4. Okay. Again, I think probably your best way, it's going to be multiple choice, so you just got to pick one that would say something like, hey, it's everybody except for this value in this case. Alright, that should take care of every problem that we have on the review guide.